Hi, and welcome to another statistics video. This one is going to show you how to build confidence intervals when you have one proportion. So anytime I start a video, I always like to do a warm-up exercise, very similar to any kind of exercise that you're doing with your body, except this one we're exercising our, you guessed it, your brain. So please pause the video and see if you can answer this question, even if you can't answer it all the way, but even just brainstorming some ideas, thoughts, meanderings, what have yous, before you hit play. Welcome back. So in this one, I always like to start off with a question again, just to get the juices flowing. So I always in statistics teach how you have some steps. You have a think part, a show, and then a tell. The think is to have you really consider what the problem is giving you. Do you have enough information? Are you making any assumptions? Because you don't want to start doing all of these wonderful maths and then be like, oh crap, I didn't even consider this as an idea. For example, notice it has a simple random sample. It was collected. That could be very important because I don't want to pull off just the M&Ms that come off the factory line. What happens if I get all yellow? So you really should have a random sample to get an idea of what the population of M&Ms in this case actually looks like. The next condition, in order to actually find probabilities, I want to estimate with a normal model. But to do that, again, I need to check a condition. Because right now, they've said a large factory batch stated 12% will be yellow. Well, I pulled 86 candies, 12% should be yellow. So is it above 10? And again, those that are also not yellow. If you're interested in that condition, I highly recommend you check out binomial distributions and how they actually apply to the normal model. But if you haven't seen those conditions before, pause the video and try to look into them and don't just accept them as fact. The show part is really what I want to focus on. So right here, standard deviation, 12%, 88 out of 86. Notice I'm calculating a z-score because again, what are the chances it is below 10% when I should expect 12%? Is that unusual? In this case, it's not that unusual. It's about 28%. And again, that number is meaningless without some context. If I just walk up to a person on the street and I say, hey, guess what? 0.284, they're going to think I need to go to an institution. They're going to think I'm a little on the cray-cray train. So always offer some kind of interpretation for your answer. Don't leave it a naked answer. Give it some juicy context. So in this case, there happens to be a 28.4% chance that in a sample of 86 candies, I can expect less than 10% will actually be yellow. Not too bad. So that idea translates over into something we call confidence intervals. And this video is going to take a look at how to construct them / create them, and really more importantly, how to interpret them. What is their meaning? Why should I build one? So confidence intervals are very, very nice because really what they do is they are a parameter catcher. Their job is to give you a range of possible values that capture the true number that you're actually looking for. But of course, the way that you build them is you get a sample statistic because guess what? You don't want to interview and you don't want to discover all the M&Ms that there possibly are to find the answer. You want to take your sample, give yourself a little wiggle room in hopes that somewhere in that range you captured the actual proportion of M&Ms that are yellow. So the way you build confidence intervals, you take your estimate and again, you allow yourself this wiggle room. We call that a margin of error in statistics. So the way that it's built is you have your p hat, which is your sample proportion, plus or minus, so there's that wiggle room. And again, that z star is a critical value. So if you've seen any statistics videos, again, feel free to pause the video to take a look at z-scores because they're absolutely important. You've actually seen this before when you saw the empirical rule, that 68%, that 95%. Those are actually confidence intervals in their own way. But what this is called is a one proportional z interval. So, and again, take a look at the margin of error. It's that last part of the formula, that wiggle room. So before we launch in, I want you to get used to calculating the z-scores because sometimes they're given to you and sometimes they're not. So whenever you see 80% confidence interval, it looks like that. It's your number up and down this amount to give you 80%. So when you calculate things in your calculator and you're trying to discover a z-score, everything gets calculated to the left of that z-score. And since I'm looking for that, I need to do an inverse norm. Notice I put in 90% because again, everything gets calculated to the left because I'm looking for that middle 80. And you should get 1.282. 90% works similarly. Notice you have 90% in the middle and then 5% on either side. So again, 0.95 to get that z-score. and that's 1.645. And you can do the same thing for 95%, and you should get 1.96 and 99%. Eventually, if you do these enough, you'll probably remember the z-scores, but I want you to be sure you understand where they're actually coming from. If you have a z-table, these are also located on there, but this is how you do them in your calculator by hand. So let's take a look at our first example. So we're going to take a look at American teens that have online profiles. In particular, do they have selfies? So we have a random sample of 487 teens with profiles found. 385 had photos of themselves. So again, three-step process to receive full credit either on an AP stat exam or just in general to be sure that you have thorough work. So every time you need to start by stating the parameters. What are you interested in finding? What is the actual number? What's the goal? And again, you're always going to check conditions/assumptions. You can't just start plugging and chugging without really thinking if your number is going to make sense and if it's going to be interpreted correctly. And obviously state the method because there's going to be a lot of different kinds of intervals that you can build. So we always want to get into practice very early. Pause the video and try to answer part A on your own. Welcome back. Hopefully for the population, you recognized it was all American teens with profiles because that's what I'm really looking at is be very specific if you can. Parameter, what's the actual thing I'm estimating? I'm interested in the actual proportion of teens with selfies. I'm going to use my sample to find that answer. Check some conditions. Random sample, yes, it says it was actually stated. So we're good there. Is it approximately normal? So 385, it says that up there, is bigger than 10, which means the remainder 102 do not have selfies, which also is above 10. And I think it's safe to say that there is population of American teens with profiles is above 400 or 4,860. And our method is a one proportional z interval. I have a single proportion. I'm using z-scores. I'm going to build my interval. All right, so let's go ahead and do a little construction. So here's my little formula. Again, my p hat is my sample statistic. So that's 385 divided by 487, which is where that 0.79 is coming from. 95% confident, so there's the 1.96. Notice the p hat gets plugged in and everything all works out. So you can calculate this by hand. It's not that it will take a long time, but it's helpful to make sure you know the formula and where it's coming from. You can also use your calculator. If you hit stat and then edit on a TI-84, go all the way over to where you see test. These are all the kinds of methods that you're going to be running, which is why it's very important that we state which one we're using. This one happens to be a one proportional z interval. Notice you can plug all your information in. I can plug in the 385. I can plug in the 487. I can even plug in the confidence interval. But notice when you hit enter, it gives you the interval already. It doesn't tell you the z-score. It doesn't really tell you anything else other than here's your interval. Notice it does give you a p hat of 0.79. So again, that's the 385 divided by 487. And interpret. So what this really is saying is that I am 95% confident that somewhere between 75.4% to 82.7% captures the true proportion of teens that have a photo of themselves. Again, somewhere in there, 95% confident that the true proportion is in there. Think of it like casting a very big net into the ocean and you're trying to capture the fish, the white whale if you want to, but hopefully not because a net, that would be a very big net. But again, it doesn't matter. You're just trying to throw it into the ocean, hopes that you capture it. You don't always, but we're 95% confident that we did. So questions like this kind of come up. Is it plausible that the true proportion of teens is maybe 75%? And explain your answer. Pause the video, try to think about this question using what we just discovered in part C. Welcome back. So here's the thing. Notice your interval. The smallest part is 0.755. Interesting. So while yes, it's possible, it would also be very surprising because we are 95% confident that the answer is somewhere between those numbers. And you're like, nah, it's 75. You're like, are you sure? Because I'm pretty confident myself. So those kinds of questions, always look at your interval to see what answer we expect to happen. And if it's outside the interval, that tends to be very unusual. So let's try another one dealing with Torchy's tacos. Pause the video and try to do this one on your own. If you can, I'd love to see you practice this before hitting the video. All right, so we're taking a look at completing dishes on time within under a minute. So this one, I wanted to show you where the p hat was coming from, just so you could really see it. So my sample proportion, so that's 60 out of 75 dishes were completed. So 80% of the dishes were completed and delivered under 1 minute. Again, think about this very carefully. I'm interested in the true proportion of dishes completed within 1 minute. That's the answer I'm aiming for. So my sample, yes, was random, approximately normal, 80% of 75. Yes, 60 is above 10, and then the remaining dishes also above 10. Yes, I'm sure the total number of completed dishes at Torchy's is somewhere above 750. Again, if you're confused about those conditions, please pause the video and look into them further. Do not accept them as fact without really thinking about it. And again, based on our formula, here's 80% plus or minus my margin of error. So again, 1.96 because it's 95% confidence. And again, I showed you the calculator steps if you were interested, but I also want to be sure that you understand the formula. And again, 95% confident that the true proportion of dishes delivered within a minute is somewhere between 70.9 and 89.1. So again, if somebody says, hey, guess what? I think 95% of the dishes are completed. You can go, are you sure? Because I'm 95% confident that it's really between 71% and 89%. So somewhere in there. Again, pause the video. Please try to do this last example on your own. Notice my words in red. Assume appropriate conditions are met. So someone did the background check. Basically, that's what you can think of it as, a background check. Also notice I've changed up the confidence level. It's now 90%. Give it a go. Welcome back. So here's the answer in case you're curious. So again, my sample proportion is 70%. Confidence interval change. Notice my z-score is 1.645 because I'm 95% confident. Check out your final answer. So we can be 95% confident that the true population proportion of fuel-efficient vehicles in the company is somewhere between 58 and 82. Not too bad. This one, again, pause the video. Try this one on your own. Notice again, this one is 99% confidence. All right, so notice I kept everything the same. The only difference is really, oh, look at that, the z-score. Notice I am more confident, so my z-score is larger. Notice it's the same sample size. Nothing has changed except the confidence. Here's the thing. When you're more confident, you're allowing a bigger margin of error to happen. Notice how big your interval just got. It now dropped to 51 up to 88, which is great. You're 99% confident. If you're more confident, you're saying, hey, to be more confident, I am going to allow more error. There's a bigger chance I'm wrong, but I'm more confident about my answer. Just be very, very careful. We don't ever want to be 100% confident, because here's the thing. It's great to be confident, but if you're not accurate, it's not really going to help. It's kind of like saying I'm 100% confident that the weather tomorrow is going to be between 0 and 1,000 degrees Fahrenheit. Is it accurate? Absolutely. But does it really give me something valuable? Is it important? Does it give me insight? Not really. It's just kind of a really silly statement. So last thing is a multiple choice kind of question. I always love asking these because it really makes you think about the concepts that we've discovered. I have put some extra words in different colors. Notice this one's not a proportion, but it still deals with the idea of confidence level. So pause the video and try to answer. All right, hopefully you got a chance to look at it. Notice I'm at 95%. I want the smallest margin of error. Well, again, if I increase my confidence to 100%, that means I've got a huge margin of error because, again, more confidence, I'm allowing more error because I need more error to make sure I'm more right. Gotta love the grammar of that sentence. Increase the confidence level. No, I don't want to do that. Decrease the confidence level. That would definitely reduce the error. Take a new sample using the same sample size. Well, no, because the confidence level is still the same. That's not going to make much of a difference. It may change the interval a little bit, but really not too much. Again, take a new sample using a smaller sample. Well, here's the thing. If I'm using less people, my answer is probably not going to be as accurate. It's going to actually, again, have more error because I have a smaller group. My answer can't be very accurate if I'm only talking to 5 people. Therefore, C is the correct answer. I want to thank you so much for watching another statistics video. I hope you have a wonderful day. Continue to watch more to see the other methods and other inference tools that we can use in statistics.